Okay, good morning. Welcome to the class. Today we're going to have a look at the second part of C1L2, which is about velocity and acceleration in two-dimensional space. Suppose you are driving south along a straight side road that has a speed limit of 60 kilometers per hour, and you stay on this road for 1 hour and then reach a highway that has speed limit of 100 kilometers per hour. You turn and travel southwest on the highway for 2 hours. So this simple example gives you an idea of why you must carefully consider how to determine average velocity in two-dimensional space. Velocity is a vector, right? And like displacement can be described in more than one dimension. A change in velocity occurs when there is a change in the velocity's magnitude, also known as speed or direction, such as the race cars taking a curve here, as shown in figure 1. Acceleration depends on the change in velocity. So acceleration in two dimensions also depends on the change in the velocity's magnitude, direction, or both. Now that you are familiar with the component method for adding vectors, you can use this method to calculate two-dimensional average velocity and average acceleration. So first, let's have a look at velocity and speed in two dimensions and then subtracting vectors. Okay, velocity and speed in two dimensions. In general, the average velocity is the change in total displacement over time and can be described by the following equation, right? Average velocity, V average, equals delta displacement over delta t. So if the displacement is in two dimensions, then you must first determine the total displacement using components, or in other words, Cartesian vectors, right? Before determining the average velocity. The notation for describing a velocity vector is the same as that for displacement, except that average velocity has units of length divided by time. So note that time is a scalar, right? It's just a number, no direction. For example, meters per second is a unit of the average velocity. So suppose a car has a displacement of 200 meters, which is shown here. The direction is 30 degrees north of east. Again, although this method is acceptable, it is recommended to use the quadrant bearing. For example, 30 degrees north of east can be written as 60 degrees east of north, right? Okay, and this car travels this distance and in this direction in 10 seconds. Then we know the average velocity is therefore given by V average equals the displacement, which is 200 meters, 30 degrees north of east, divided by the 10 seconds, which is 20 meters per second. Direction is 30 degrees north of east, which is the same with your displacement, right? So what happens when there are several displacements, though, each with a different direction? The average velocity for the entire trip is based on the total displacement. Therefore, the average velocity will always have the same direction as the total displacement. So in this situation, in this equation, the average velocity equals total displacement over delta t. And we have delta t equals delta d1 plus delta d2 plus delta d3, and so on. To use this to calculate the total displacement. Add the horizontal and vertical components of the individual displacement, and then combine them to obtain the magnitude and direction of the total displacement, as in section 1.3, which we have already discussed yesterday, right? Okay, so now let's consider the average speed. Note that speed is a scalar, right? It's not a vector, so it only has numbers. On the other hand, if you consider average speed, which is a scalar property based on the length of time traveled and total distance traveled, regardless of the direction. Therefore, when an object returns to its starting point, the distance it has traveled is the sum of all displacement magnitudes and is thus not zero. So be careful with the definition of average speed. Average speed is total distance traveled divided by the total time to travel the distance, which is given by this formula. Average speed, which is usually noted by V average equals delta D over delta T. All of the three quantities are scalars, not vectors. So average speed is simply this total distance divided by the time of travel, and it's greater than zero. Okay, remember it's always always greater than zero. Okay, so now let's have a look at a sample problem to illustrate these concepts. Okay, let's consider a problem here. A family drives from St. John, New Brunswick to Moncton, assuming a straight highway. This part of drive has displacement of 135.7 kilometers. Direction is 32.1 north of east. From Moncton, they drive to Amherst, Nova Scotia. The second displacement is 51.9 kilometers. Direction is 25.9 south of east. The total drive takes 2.5 hours to complete. Answers following two questions. First, calculate the average velocity of the family's vehicle. Then calculate the average speed of the family's vehicle. Okay, so according to what we have discussed, I'll give you 5 minutes to consider this question by yourself first, okay? Okay, have you finished? All right, let's have a look at something together. Okay, so for question A, okay, let's have a look at question A first. In question A, we are given the first displacement delta D1 is 135.7 kilometers, direction is 32.1 north of east, right? And also we're given the second displacement, which is 51.9 kilometers, 25.9 south of east. And time interval is 2.5 hours. And we need to find the average velocity, V average. So we can make a scale diagram to show the situation. Determine the components of the two vectors, then determine the total horizontal displacement, delta dtx, which is delta d1x plus delta d2x. And similarly, the total vertical displacement, delta dty, which is the sum of the two components for delta d1y plus delta d2y. Then calculate the magnitude of the total displacement using the Pythagorean theorem and use the inverse tangent equation to calculate the angle of the orientation for total displacement. The average velocity is then total displacement divided by the time of interval. Okay, so we can draw a diagram like this. The longer vector here is our delta d1, and the shorter vector here is delta d2. Then using vector addition, we can find first of all, we need to resolve these two vectors into the x and y axis, right? Then we know delta d1x is delta d1 times cosine theta 1, and delta d2x is delta d2 times cosine theta 2. And put all the numbers in, we have delta dtx is 161.6. The unit is kilometers. And direction of delta dtx is, of course, a positive direction, which means the east. And then we find the total displacement in the y-axis. Delta dty is the sum of delta d1y plus delta d2y, which is delta d1 times sine theta 1 minus delta d2 times sine theta 2, according to this diagram. And this gives us delta dty equals 49.44 kilometers. Direction is north. Okay, then if you have the components for the total displacement, which is 161.6 and 49.44, then we can find the magnitude of this vector, right? As shown here. The magnitude of the total displacement is the square root of the sum of the two components squared, which is approximately 169.0 kilometers. And the theta t in this diagram is arctangent delta dty over the magnitude of the delta dtx, which is about 17 degrees. So the statement is here. The total displacement is 170 kilometers. The direction is 70 degrees north of east. And average velocity is therefore given by total displacement over the time interval, which is 169.0 kilometers over 2.5 hours. Well, actually, this should be 170. So please correct this number here. And the final solution is average velocity is 68 kilometers per hour. So direction is 17 degrees north of east. Okay, so this is just one type of notation which you can use to solve this problem. And now let's introduce the second method, which is to use another notation system. It is recommended to use this type of notation here, because personally, I think this notation here is much more clearer than the previous one. Okay, so in the second method, first, we can express the first displacement delta D1, which is given by 135.7 kilometers. Direction is given by 32.1 north of east, right? So we can draw a diagram on a scratch paper and find two components for the first placement, which is 135.7 times cosine 32.1. And the y component is 135.7 times sine 32.1 degrees. And then the two components are 115.0 and 72.11. So here I just keep 4 significant figures for these two components. And then the unit is kilometer. So we can use the same method to find the second displacement in Cartesian vector. So if the direction of the second displacement D2 is 25.9 south of west, then we know the angle D2 makes with the positive x-axis should be negative 25.9 degrees, right? So we can resolve this displacement into x and y directions. So the two components are 51.9 cosine negative 25.9 degrees. And the y component should be 51.9 times sine negative 25.9 degrees. So be careful with the sign in front of your angle, whether it's positive or negative. You need to draw a diagram to find corresponding angles, okay? And then the two components are 46.69 and negative 22.67. Again, the unit is kilometers. So the negative symbol here indicates the y component of the second displacement is in accordance with the negative direction in the vertical axis, which means due south, right? Okay, so if you have resolved delta D1 and D2 into x and y directions, then the total displacement, which is denoted by dt, is given by D1 plus D2, right? Also note that this is an addition of two vectors. So if you can use the Cartesian vectors for D1 and D2, we can just add their x components and y components respectively. So the total displacement dt is 161.7 and 49.44. These are the two components for the total displacement. Again, this is in Cartesian form to represent a vector. The unit is kilometers. So this method we have learned in our calculus and vectors class, right? Then you can find the average velocity VAV, which is dt's total displacement over the time interval t, which is given by 1 over 2.5 times the vector for dt. So just put these two components in. This gives you the average velocity. In Cartesian form, this is 64.68 and 19.78. Again, I just keep 4 significant figures for this vector here. And the unit here should be kilometers per hour. So if you know the two components for a vector, then you can find the magnitude of the average velocity, right? The magnitude of the average average velocity should be the square root of the squared x component plus squared y component, which is approximately 67.64, which is approximately 68 kilometers per hour. Then remember, velocity has direction as well. So next we can find the direction of the average velocity. We can let theta denote the angle the average velocity makes with the positive x-axis. Note that angle could have unlimited number of solutions, right? As long as they are coterminal angles. The values for theta could be unlimited. As long as you can find one of the possible solutions, you'll be fine. So note that according to the definition of tangent theta should equal the y component over the x component of dt, right? So just put these two components in. Sorry, here. You can make a modification here. Well, these two numbers denote the components for all velocity. So I'll correct it to the velocity, although they are the same. Okay, let's use velocity here. Okay, so tangent theta is given by VTY over VTX, which are the y component and x component of VT. Oh, sorry. Well, if we use the components for V, there is no need to write T here. So just to use V, Y, and Vx. To denote the two components here. Okay, so tangent theta is given by the ratio between the y component of average velocity and the x component of the average velocity, which is 19.78 over 64.68, which is approximately 0.3058, right? And we also know, okay, let's make a correction here. So this should not be D, although they are the same. So here we are using VAVX, which means the x component of average velocity. And change this to V and average velocity in the y axis. Okay, this seems clearer. All right, so we know tangent theta equals approximately 0.3058, right? Also, we know the x component of the average velocity is greater than 0, and the y component of the average velocity is also greater than 0. So we know theta must be in the first quadrant, right? So we can find one possible solution, which is arctangent 0.3058. And this angle should be around 17 degrees. Therefore, the direction of the average velocity in quadrant bearing is given by 73 degrees east of north. So we can make the final statement because we know the magnitude and the direction. So the average velocity of the vehicle is approximately 68 kilometers per hour. The direction is 73 degrees east of north. Okay, have a look at this method. Do you have any questions? So you can choose either one you like. So basically they can have the same solution, right? Both of them have the solution 68 kilometers per hour and direction is 73 degrees east of north. Okay, if you have no questions, let's have a look at question B. So in question B, we're given delta D1 is 135.7 kilometers. Direction is also given. So for delta D2, also we know the magnitude and direction. And delta T is also 2.5 hours. So this time we want the average speed, right? Which is denoted by V average. So average speed is total distance traveled over the total time used. So first of all, we find the total distance traveled, which is the sum of two magnitudes of the two displacement, right? So first, let's calculate the magnitude of delta D1, which is 135.7 kilometers. You can just put the numbers in, right? And magnitude for the second displacement is 51.9 kilometers. So the total distance traveled of the vehicle is 187.6 kilometers. Then the average speed is this number divided by the total time used, which is 2.5 hours. And then the average velocity is approximately 75 kilometers per hour. So we can make the statement, the average speed of the vehicle is 75 kilometers per hour. So as you can see here, to calculate the speed is much easier than the velocity, right? Because you don't have to consider the directions. Just use the total distance traveled divided by the total time traveled. Then you will get the average speed of the vehicle. Okay, any questions? No? All right, if you don't have any questions, let's have a look at the next one. Well, this is to illustrate how we can subtract vectors in 2 dimensions. Well, actually, we have talked about this a lot in vectors and calculus class, right? Okay, so let's revisit this concept again. So up to now, you have been working with vector addition. In some cases, though, we need to multiply vectors by scalars and subtract vectors. Before dealing vector subtraction, first consider the multiplication of a vector by scalar. Scalars are simply numbers such as 2 and 5.7 or 3 or 4 or 5 and so on. Multiplication of a vector by a scalar changes vector's length or magnitude, does not change directions. If a scalar k is greater than 1, then the product of k and vector a is longer than a, right? Similarly, if k is between 0 and 1, then the product of k and vector a is shorter than the original vector a. So now suppose the scalar k is a negative number, where k is smaller than 0. If we multiply vector b by k, then vector b and kb point in opposite direction, right? So basically, that means if you time a negative scalar to a original vector, that changes direction to the opposite of the original vector. So now you can see how vector subtraction arises from scalar multiplication and vector addition. Subtracting vector b from vector a is actually equivalent to adding the vectors a and -1 times vector b, right? So for k equals -1, let's see figure 2 here. Expressing this as a vector equation yields vector a plus -1 times vector b equals vector a minus b. So we have already know how to do vector additions, right? So we can use this same approach with the components of vectors. By multiplying one component by an appropriate negative scalar, you can subtract two vectors components in one dimension by adding the positive component of one vector and negative component of the other vector. So what does subtracting vectors mean physically? When a vector changes over an interval of time, the physical quantity of interest is the measure of the change, or the difference between the vectors in that time interval. For example, consider a car following a curve on a level road, as shown here in figure 3 on the right. Even if the driver keeps the speed of the car constant, the direction of the car changes. This change equals the difference between the velocity at one point in time and the velocity at any earlier point in time. In other words, the change in velocity is a subtraction of the final and initial velocities, which is given by delta v, which is the difference in velocity, equals the final velocity subtracted by the initial velocity. So note here in this formula, all the three quantities are expressed in vectors, which means they have both magnitude and direction. So you cannot simply put their numbers in, okay? You need to use vector addition and subtraction to find delta v. All right, so next let's discuss the acceleration in two dimensions. So all the previous work are the basics to find acceleration in two-dimensional space, because according to the definition, the average acceleration is delta v over delta t. Delta v is also vector, right? So first of all, you need to know how to find delta v, which means you need to know how to do vector subtraction. Okay, so we now can apply the principle of vector subtraction in two dimensions to determine the average acceleration in two dimensions. Recall that acceleration in one dimension is a change in velocity over time, which is given by average velocity equals average average acceleration equals average the delta velocity, velocity difference over delta t, time difference, which is final velocity minus initial velocity over delta t. The average acceleration occurs when the velocity vector of an object changes in magnitude, direction, or both. So as with two-dimensional displacement vectors, you can break down the two velocity vectors into horizontal and vertical components by subtracting each dimension's components. We can obtain the net horizontal and vertical components. For example, delta x equals vfx minus vix. And delta vy equals vfy minus viy, which basically means the x component of delta x equals the difference in the x aggression, and the y component of the delta v is the difference of the final and initial velocity in that direction, right? From these, then we can calculate the magnitude and direction of the net velocity using either the Pythagorean theorem or the definition of trigonometric ratios, and together with inverse tangent equation. So basically, we have the following two formulas. First, the magnitude of your delta v equals the square root of the squared delta vx plus the squared delta vy. So basically, the squared x and y components respectively, right? And then tangent theta is delta vy over delta vx, which is a ratio between the y component and your x component. And also note that theta is the angle that delta V mix with the positive direction of x-axis. So theta could have unlimited number of solutions, right? So you need to determine the actual value of theta according to the context of that problem. And then finally give a quadrant bearing or true bearing of the direction of delta V. Then to calculate the average acceleration using your delta V over delta T, that gives you the average acceleration. So basically, the average acceleration should have the same direction with your delta V, right? Okay, so these are the basics to calculate the acceleration in 2 dimensions. Now let's have a look at a concrete example to illustrate this concept here. Okay, consider this problem here. A car turns from a road into a parking lot and into an available parking space. The car's initial velocity is 4 meters per second. Direction is 45 north-east. The car's velocity just before the driver decreases speed is 4.0 meters per second, and direction is 10 degrees north-east. Also, the turn takes 3.0 seconds. Can you calculate the average acceleration of the car during the turn? Okay, again, I'll give you 5 minutes to have a look at this problem here. Okay, remember, you can always resolve the vectors first, find the 2 components, then find magnitude and the direction. All right, have we finished? Okay, let's have a look at the solution together. Okay, so according to given information, we know the initial velocity VI is 4.0 meters per second. Direction is 45 degrees north-east. And this can be expressed in Cartesian form as x component is 4 times cosine 45. Y component is 4 times sine 45, which is approximately 2.828 and 2.2828. So here I just keep four significant figures here. Unit is meters per second. And final velocity is VF is given by magnitude is also 4 kilometers. And direction here is 10 degrees north-east. So this can be expressed as 4 times cosine 10 degrees, 4 times sine 10 degrees, which is 3.939 and 0.6946. And unit is meters per second. And then we can know the velocity difference is delta V given by VF minus VI. So we can use the Cartesian form of VF and VI. The difference in x direction is 1.111. Difference in y direction is negative 2.133. And unit is meters per second. Then the average acceleration, A average equals delta V, which is the difference of velocity over time interval t. We know the time interval is 3 seconds, right? So that equals 1/3 times the 2 components of delta V is 1.111 and negative 2.133. And this gives us approximately 0.3703 and negative 0.7110. This is the Cartesian form of our average acceleration. The unit is SI unit, meters per second. Oh, sorry, meters per square second. Then if you know the two components of the average acceleration, you can find the magnitude of the average acceleration, right? The magnitude of the average acceleration is the square root of the squared x component plus the squared y component, and this gives us approximately 0.8017 meters per square second. Then we need to find the direction of the average acceleration. We can let theta denote the angle the average acceleration makes with the positive x-axis. Again, there are many possible values for the solution of theta. So as long as you can find one, you should be you should be fine. So according to the definition of tangent theta, we know tangent theta is the y component of average acceleration over the x component of the average acceleration. So put both of numbers in. This gives us negative 1.920. Also, we know the x component of the average acceleration is greater than 0, and y component of the average acceleration is smaller than 0. So we know theta must lie in the fourth quadrant, right? Then one possible solution is given by theta equals arc tangent, negative 1.920. Remember, arc tangent is an angle between negative half pi and half pi, right? So if you find an angle which is negative 62.49, this angle is in fourth quadrant, that should be fine. Therefore, you can draw a sketch on a scratch paper, then find the direction of the average acceleration, which is in quadrant bearing, is 27.51 east of south. Then we can make this final statement like this. The average acceleration of the car is approximately 0.8017 meters per second, and followed by a direction 27.51 degrees east of south. Again, this is in quadrant bearing. Okay, have a look at this question. Do you have any questions? No? Okay, if you don't have any questions, remember to complete your homework in Google Classroom and submit before the deadline, okay? And I'll see you next time. Bye.